All right, welcome to The Explainer. Today we're going to tackle a concept that sounds like something straight out of science fiction, but is, and this is no exaggeration, the absolute bedrock of our modern world: complex numbers.
So picture this. It's the 1500s, and mathematicians like Girolamo Cardano are hitting a brick wall. They're trying to solve certain equations, but they keep getting these bizarre results that require taking the square root of a negative number, which they describe with phrases like, well, this one.
I mean, it seemed completely impossible, right? A mathematical dead end. You square a positive number, you get a positive. You square a negative number, you also get a positive. So how could you ever get a negative result? Well, what changed wasn't the math, it was the perspective.
So this whole mess, it really kicked off with polynomial equations, something like this one that Cardano was wrestling with.
And this is what was so maddening about it. The equation had a perfectly real, perfectly sensible solution, 4. You can check it yourself. But the general formula, the very tool designed to find that answer, forced them through this bizarre, impossible territory with things like the square root of -121. It's really no wonder they dismissed these steps as, quote, as subtle as they are useless.
But then, a few brilliant minds started asking a different question. What if these numbers weren't a mistake? What if they were a doorway to a whole new dimension of math?
So, in the 16th and 17th centuries, mathematicians like Raphael Bombelli and René Descartes did something kind of radical. They just decided to stop fighting it and define a solution. They said, okay, let's just create a symbol for the square root of -1. We'll call it I, the imaginary unit.
And this one little idea, it blew the doors wide open. It meant that numbers didn't have to live on a single line anymore, just going left and right. Suddenly, they could exist on a whole two-dimensional plane with a real axis and this new imaginary axis.
And this brings us to the key insight. I isn't just a number, it's an action. It's a rotation. Multiplying by I is like taking a number on that real line and literally turning it 90 degrees perpendicular to where it was before.
Thinking of it as real and imaginary is really no different than using east/west and north/south on a map. They're just labels for two totally distinct perpendicular directions. That's it.
Okay, so we've got this whole new mathematical playground. How do we actually navigate it? Well, this new way of thinking leads to what many people call the most beautiful equation in all of mathematics.
The secret sauce here comes from this hidden connection between three of math's biggest heavyweights: the exponential function e and the trig functions cosine and sine. See, under the hood, each of these can be built up from an infinite string of simpler terms. And the real magic happens when you ask, what if we plug an imaginary number into e's series?
When you do that, something absolutely incredible happens. The terms in the series for e magically rearrange themselves into the series for cosine plus I times the series for sine. You get this phenomenal result, Euler's formula. It's like a Rosetta Stone, connecting exponential growth directly to waves in circles. And what's so cool is that Euler's formula isn't just a static equation. It describes movement. As that angle, theta, changes, the formula traces out a perfect circle on that complex plane. This is, at its core, the mathematics of anything that rotates or oscillates.
And if you set that angle theta to be pi, or 180 degrees, the formula simplifies into this stunner: Euler's identity. It just elegantly links the 5 most fundamental constants in all of mathematics: e, I, pi, 1, and 0. It's just perfect.
Okay, so this isn't just some beautiful abstract math game. Here's the crucial point. This is the actual language of the physical world, especially when things start to wiggle or wave.
So think about a really simple physical system, right? A mass on a spring. It bobs up and down, it oscillates, but friction or damping makes it lose energy over time. And that motion is described by a specific kind of math called a differential equation. Now, let's look at something that seems totally different: an AC electrical circuit. You've got a resistor, an inductor, and a capacitor. Well, guess what? The flow of charge also oscillates back and forth, and it's dampened by the resistance in the circuit. And here's the kicker. When you actually look at the math describing these two systems, they are identical. The mass in the spring system behaves exactly like the inductance in the circuit. The damping from friction is just like electrical resistance.
Complex numbers give us one single, unified language to describe how things oscillate in completely different corners of physics.
And that unifying power, it's not just some neat party trick for physicists. It's the very reason this math is almost certainly running inside the device you're using to watch this right now.
Wi-Fi, GPS, the music you're streaming, all of that is just information encoded in waves, and the easiest, most efficient way to describe, create, and manipulate those waves is by using complex numbers, powered by Euler's formula. Because using them turns really messy, complicated trigonometry into simple arithmetic. It's like a massive shortcut. You need to shift a radio signal from one frequency to another. That used to involve a bunch of painful trig identities. With complex numbers, it's just a single, simple multiplication. This is the engine that makes digital signal processing, DSP, so incredibly powerful. And here it is, out in the wild. This isn't some theoretical drawing. It's a practical blueprint from a real-world software-defined radio. See that block right there, labeled complex multiply? That's the engine, doing exactly what we just talked about, multiplying a signal by a complex number to tune to exactly the right frequency.
So yeah, think about that. A concept that started out as mental torture and was dismissed as useless is now the indispensable mathematical tool that powers our entire digital connected world. It really makes you wonder, doesn't it? What seemingly useless or impossible mathematical ideas are being explored today that will become the engine of tomorrow's technology? Thanks for joining me on this explainer.